So I guess you started talking about integration, so I thought we would just go ahead and practice with iterated integrals and change of variables. It's kind of fun computational stuff. Okay. So if you have, and we're going to talk about regions. I guess for now he's just sticking to 2 dimensions. So regions in the xy plane. So what does it mean for a region to be x simple? So you have D is a subset of R2. What does it mean to say that D is x simple? What is that in set notation, and I guess in pictures or words? What does it mean? You can use your mics. Oh, I need to record this. Did somebody press the record button for me? That's right, the bounds. So this means that the bounds for y are bounds can be expressed in terms of x. The bounds for what? So x is between 2 numbers, and y is bounded by functions of x. So those are going to be like nice differentiable functions. So obviously you have that x is bounded by 2 horizontal lines, but y is bounded by functions of x. So y equals h of x and g of x. That's D. Okay, good. And so it's just as simple then to define D as domain being y simple, of course. It's just a domain or a region that can be described by y being between. I have no idea why I use D. So now y is between 2 numbers. And then x is bounded by 2 functions of y. So we have 2 horizontal lines where y is a constant. And then x is bounded by 2 functions of y. A simple enough concept, right? All right. So let's see. So let's try this iterated integral. So suppose we have an integral. Say we're integrating 2 times y. It doesn't really matter. Okay. And they say, well, can we first of all write this as a single integral if we switch the order of integration? Okay. So can we write this as a single integral if we switch the order of integration? So what are we asking there? Well, if you can switch the order of integration and still have a single integral, then the region you're integrating over has to be both x simple and y simple. So we can check whether the region of integration, the xy plane, is both x simple and y simple. Okay, so can you sketch the region of integration? So the way this is written, is it written like a x simple or y simple region? Okay, so what are the bounds for x? Think of these as like nested integrals. Yeah, it's written, yeah. So x is between 0 and 1. Those are the x bounds. So x equals 0, another name for the y-axis, and x equals 1. And then we see that the bounds for y are 0 to the square root of x. Okay, so below, y is bounded by the horizontal line where y equals 0. And above, y is bounded by the function where y equals square root of x. Okay. And so we would have to be able to sketch this region to see, yeah, it's, if we would switch the order of integration, so we're going to treat this as the other type of simple region. So we're going to have dx dy. So what would the bounds for y be? Zero to 1. Y goes from 0 to 1. And what would the bounds for x be? Zero to y squared. So x goes from 0. So x, you're saying, is bounded. I can't believe I'm so happy that you made this mistake. That's so terrible. That's just so wrong from actually. But I find pleasure that you got that wrong. Yeah. So if you say that x is between 0 and, well, y squared, so where is x equal to 0? That's the y-axis. And where is x equal to y squared? Well, you know that that's exactly this curve, just where you solved for x, right? You went, okay, I'll just square both sides. X is positive, so no. Okay. But the problem is that if x is between that vertical line and that curve, you're integrating over this region. If you look at the original region, what was y between? Well, y was between y equals 0 and the curve where y equals square root of x. So y is between those two curves. So y starts at 0 and increases till it hits the curve. So you actually chose the wrong region if you choose x to be between 0 and y squared. So what should we have chosen the lower bound for x to be? Okay. So when integrating with respect to x, think about the region that you need to cover. Identify the region that you're integrating over. This is the region. And then draw horizontal lines, because x, when you're integrating with respect to x, x is changing. And as you draw those horizontal lines, On which curve does x start? Yeah, thank you. Very good. All right. So x starts on the curve where x equals y squared. And then it increases until it hits the vertical line where x equals 1. So very good. And then you can integrate. So might as well finish this, I guess. Okay, so we integrate with respect to, sorry about that jumping. So we first do the integral with respect to x. So y is being held constant when you're integrating, finding the antiderivative with respect to x, so that's just 2yx. As x goes from y squared to 1. And if you kind of get confused, just remember those are x bounds, so you're going to be replacing x. At the upper bound, x is 1. And minus at the lower bound, x is y squared, so we get 2y cubed. And then you know how to integrate. So you get 1/2. Okay. All right. So let's do another one of those. But this time, you might be simply told to. Okay. So our next example, we're going to be simply told to evaluate. Let me just see if I can cheat this whiteboard. There you go. Stupid whiteboard. Okay. Aww. There you go. So suppose you're simply asked to evaluate the following integral. Okay. So what's the... Yeah, if the function is hard to graph, yeah, I don't know. It's very hard. Okay. So what's the problem with the integral as it is? Like, why can't we even try? Like, I guess we could try, but what goes wrong here when we try to evaluate the iterated integral? Well, when we can't, right? There you go. Thank you. Yeah. So if we try to integrate with respect to y, well, we just don't know how to find the antiderivative there. Like u sub doesn't work, whatever. So we can try all sorts of things. It wouldn't work. So what can we try instead? Well, switch the order of integration and see if that way. Polar? That would be interesting. But let's see. So I usually think of polar if you... Yeah, we'll see. Let's draw the region of integration. So, okay, what are the bounds for x and what are the bounds for y? Okay, so what are the bounds for x? 0 to 2. And what are the bounds for y? Well, y at the lower bound is x cubed. Y at the upper bound is 8. So can we sketch the region of integration? Well, x0 is just your just the y-axis. X equals 2, we know what that looks like. Okay, now what about at the lower bound for y? Y would be x cubed. So we kind of know what that looks like. It's like something like that. The cubic, right? It keeps going. Okay. At the upper bound, y equals 8. So y equals 8, we know, is a vertical line that happens conveniently. Okay, so which region are we talking about then? Is it region 1 or region 2? Which is our region of integration? Region 1, that's right. Because y starts on the curve where y equals x cubed and then increases till it hits the line where y equals 8. So if you draw these vertical lines, you see that we're mowing the grass, so to speak, from south to north. So that's our region of integration. So if we were to switch the order of integration in this iterated integral, what would the bounds for y be? Yes, very good. So y would go from 0 to 8. Okay, and what about the bounds for x? Okay, very good. So clearly, so now we're mowing the lawn from west to east, right? So x starts on a line where x equals 0. It increases till it hits this curve. And what is x equal to on that curve? Well, just solve for x, right? Take the cube root both sides. So this is somewhat contrived, right? Because like who's really integrating this thing in real life? Like what is it used for? But okay. So now the idea is that okay, now the integral, this inside integral, so to speak, with respect to x is quite doable. Because when we're integrating with respect to x, we're holding y fixed for the time being. So that just becomes x times this function of y, integrating with respect to x. And the bounds for x are 0, 2, and yeah. So we get at the upper bound, at the lower bound of x is 0. So there you go. And now you see that here, in fact, it turns out that this integral is quite doable. Cool. So maybe you do a u sub. We recognize that this is proportional to the derivative of the exponent. So maybe let y equal 4/3. So u equal to y to the 4/3. So du is dy. So 3/4 of du is. Okay, so let's do this to change a variable. This portion is equal to 3/4 of du. And then we get e to the minus u. Okay. And what would the bounds be in the new domain, the u domain, so to speak? Yeah. So what's the lower bound for u and what's the upper bound for u? So when you do when you start doing change in variable for double integrals, yeah. So we reason that, okay, when y is 0, you use this change of variable, so u has to be 0 when y is 0. But when y is equal to 8, then you get cube root of 8 as 2. 2 to the 4 is 16. So very good. All right, so anyway, we get our integral. Here's our antiderivative. E to the minus 16 minus 1. So whatever that becomes. Okay, very good. All right. So what's next? All right. Okay, so now let's suppose we want to find volume. Let me just clear this out. Okay. So now suppose we want to find the volume okay, between the xy plane and the cone, where z is equal to the square root of x squared plus y squared. In the region of the xy plane that's bounded, let's see, let's say, can we say this, that's in the first quadrant. Okay. Outside the circle, below the line, y equals 1, but above the line, y equals x. And this below line, above line, I'm just playing games, right? So it should be in the, you can say it's like the intersection of these kind of inequalities. So all the points below the line means all the points where y is less than 1. Above this line means it's all the points where y is greater than or equal to x. Okay. All right, so where do we start? What do we want to do first? Yeah, I would draw the region so we're clear. So, okay, so let's describe this region in the xy plane, or draw it, or sketch it, or whatever. Okay. So let's say we're in the first quadrant. Okay, well that's gonna. Okay. So x and y are positive. We're outside the circle, so that's a circle. It's our unit circle at the origin. below the line y equals 1. So y equals 1 is a horizontal line. And above the line y equals x. Okay. So I'll give you some options. Region 1, region 2, region 3, region 4. Yes, region 5 and region 6. Which region are we talking about? Region 1. So it's not region 1, so which condition is contradicted by that? Yeah, that's right, outside the circle. So it can't be region 1. Or region 4 for that matter. It's region 2, that's right. So we're below the line. So if we start shading below the first quadrant, below the line. We also have to be outside the circle. And above that diagonal line. So kind of cheesy, but yeah. So the only region that satisfies all those inequalities or conditions is region 2. So, that's right. Okay. So is that region going to be? Would you say it's x simple or y simple? You have to tell me. I forget. You know, I'm kind of like a dyslexia thing. I don't know if it's x simple or y simple. Like, I don't know what that means. So is this blue region that we're going to be integrating over, is that x simple or y simple? Let's zoom in. So this is our domain of integration. Well, so which variable is bounded by two curves, and which variable can be thought of as being bounded by two lines, two constants? Right, so if we try to say that, okay, x is bounded between two functions, so we draw these vertical lines. And sure, here x is bounded by the circle below and by this horizontal line above. But as you move over, you see that the lower bound for x changes. So you couldn't say that x is bounded by a single function below, and it's bounded above by 1. But it's not bounded above by a function, just a single function below. So x would be between two lines, right? Sorry, y would be between two. Y would be between two lines. Sorry, my bad. Okay, y is not. It's bounded above by 1. I apologize. But it's not bounded below by a single function, right? So x, as you were saying, I apologize for that. X is y would be bounded by two lines, and x would be bounded by two curves. Well, okay. So we can say, what's this point of intersection between the circle So we have our circle, and we have our line. So what's the point of intersection? Yeah. So we have x squared plus y squared, where y equals x. So we just substitute, and we get 2x squared is 1. So x is going to be plus or minus 1 over root 2, and we're in the first quadrant, so we take the positive version of that answer. Okay, and so this point of intersection is 1 over root 2, 1 over root 2. So we can say that y is between square root of root 2 and 1. So y is bounded by 2 horizontal lines. And then x is bounded by 2 functions. Okay, what's x equal to on the line below? Oh, sorry, the curve on the left. Just remember that curve is given by the equation of a circle, the graph of a circle. So can we solve for x as a function of y on that circle? Yeah. So again, you have your circle, just solve for x. So x is plus or minus the root. Okay. And of course, x is positive, so this is the lower bounding function for x. And what's x bounded? What function of y is x bounded by to the right? X equals y. So in this kind of region where we say the domain of integration here is all points where the y values are between constants or two horizontal lines, and x is bounded by 2 functions of y. Did we call that x simple or y simple? And I really always forget whether it's, I think it's called y simple, right? Is that correct? Y simple, yes. Yeah, so y simple. Is it y simple? Yeah. Simple in the sense that the bounds for y are simple, I guess. Okay. So, and how is that related to finding volume? Right. Between the xy plane and the cone. Okay, so we have our funky region, the xy plane. This little tiny bit. And then we have a cone. And we want to find the volume underneath that cone, just over that tiny region. I don't know if that makes sense. Yeah. So the xy plane, so if this, that region between the cone and the xy plane is like a house, the cone is like the roof, the xy plane is like the floor, then we have walls. Yeah. Right, so we can find the volume by just integrating over our region, our domain of integration. And then we just take the difference between the height, so the roof minus the floor. So that just be the equation of the cone gives you the height. Z equals x squared plus y squared minus the floor where z equals 0. Okay. And now that we found that our region of integration in the xy plane is y simple, we know that we would be integrating with respect to y as y goes from, then integrating with respect to x as x goes from one curve to the other. And this is what we're integrating. All right. Now, I really don't want to integrate this. So what's the other thing that you talked about in class? So if you have a surface, let's say where z is positive, so z is a function of x and y, and we're looking at the graph of that, but we're going to assume z is positive. Well, of course. And you want to find the volume between the region in the xy plane and the surface. It's terrible. Yeah, I need to redraw that. Okay, so we're trying to find the volume of this object. You can think of it as you have a differential amount of area in the xy plane, and then you multiply that by a height given by the value of the function. The z value is the height. And that gives you the volume of like a rectangular box. So that volume would be the height times the differential amount of area in the xy plane. And then if you want to add it all up to get the total volume, well, it's integration. Okay. So that would give you the volume between the surface there and the xy plane. Okay. All right, how much time do we have? Okay, let me see. So, and I don't want to integrate this, right? So what could we do to actually evaluate this integral? Yeah, polar coordinates, that's right. So we have a region in the xy plane, kind of not the nicest region. What would the corresponding region be in the, say, theta r or r theta plane? And so if this is region D, we want a corresponding region D star. Switch the order would work? I don't know about that. But I'm thinking polar because, first of all, there's a square root of x squared plus y squared, which simplifies nicely in polar. And also, there's some sort of radial thing going on because of the circle. So what would the bounds for theta be if we did this in polar? It wouldn't be 0 to 2 pi. Because remember, in polar, we're going to let theta is the angle, of course, from positive x-axis. So there's a starting value of theta, and theta is going to increase until we hit some maximal value of theta, so that we're covering this region in terms of theta. So when we're on this slanted line, what is the value of theta for y equals x? Yeah, very good. So pi over 4 is the starting value of theta. And then theta increases, right? And so until we get to till theta gets to pi over 2. And that ensures that in terms of theta, we're covering our region D. Yep. Very good. Okay, so now what about R? What are the bounds for R? Okay, well, let's start with the lower bound for R. It's 0 to 1. So remember, R is like the distance from the origin. So if you did R goes from 0 to 1, what would happen? Well, R starts at 0. Right, so if we're doing 0 to 1 for R, and R increases till it hits the until it's a distance R 1 away from the origin. So we'd be covering the wrong region. We'd be covering the inside of that circle, not the outside. That can't be it. So wrong region. This is inside the circle. We need to be outside. So what's the lower bound for R? So you're sweeping out this region in a radial fashion, right? So theta is something. We want to cover region D. So draw radial lines. And what's the starting value of R? Okay. So R, in a sense, starts on the circle. So what is R equal to on that circle? Yeah, 1, that's right. So R starts, when we're starting on the circle and drawing these radial lines. So we're starting at points where we're one distance away from the origin. So R equals 1 at the lower bound. Okay, so what about the upper bound? What's the maximal value of R? Okay, that's a little tougher, right? So because there, the greatest extent that we're away from the origin is changing with theta. So if we draw a line where y equals 1, and we draw a line like this, and this is theta, what can we say about this hypotenuse? This will represent the maximum value of R, maximum distance. Can we write the maximal value of R as a function of theta? Okay, so yes, so in this right triangle that we drew, we're assuming theta is going to be given to us, right? If we know theta or something, and we know this side is length 1 because that's the height, yeah, the distance of 1. And we want to relate theta to the hypotenuse, so that's the maximum R value. So we can use, and we know the opposite side, so of course we're going to use sine. Sine of theta is opposite divided by hypotenuse. So it looks like the upper bound for R is going to be a function of theta. Okay. So here we would say, okay, if you try to draw this region, theta is between pi over 4 and pi over 2, and R is between 1 and some something greater than 1, right? So it's a curve, it's a function. So r equals 1 over sine theta. It's part of the graph of cosecant of theta. So it's going to look something like, I don't know what that is. So, I don't know, it's some curve. I am lying, so that's 1. So this is the graph, part of the graph of cosecant, essentially. So this would be the region D star, corresponding to D. So let's make it orange. Okay, so is that theta simple or r simple? Would you call D star theta simple? Or r simple? Yeah, theta simple. Yeah, r is bounded between a function of theta. So anyway, so now we would do the change of variables. Now I'm not going to do the Jacobian thing here. We'll just use the fact because I'm going to move on to that. So theta goes from pi over 4 to pi over 2. And r goes from 1 to 1 over sine theta. And what was the function we were integrating? It was square root of x squared plus y squared. So in polar coordinates, it's exactly equal to r. And what is the differential area element in polar coordinates? That's right. Yeah. It's r d theta. So then this integral is then doable, I guess. So yeah, I think it's going to be the integral of cosecant cubed. So I'm not really happy about that. Yeah. So you get r squared. Integral of r squared is 1/3 of r cubed. At the upper bound, that becomes cosecant cubed. Yeah, so that's the well-known integral. And I'm not going to do it. Easy, yeah, easy peasy. Yeah. All right, what's next? All right, so we want to go over change of variable formula for double integrals. Okay. So the idea is to have a region in the xy plane that you want to integrate over. And so by a change of variable, and so if you'd like, it's a direct substitution where we're going to let x and y be a function of, let me write it another way, sorry. Well, that's right. A function of u and v. So you have the uv plane. And either we want to do a change of variable to make this region of integration in the xy plane correspond to a simpler region the UV plane, so the region of integration is simplified. So we have that this function maps d star into d. And so one reason you want to do that is because d star is a simpler region than d. Other times you want to do this change of variables so that the integrand becomes simpler, right? That's another consideration. Okay. And so the change of variable formula says that, okay, when you do the change of variable, you're going to have an integral in terms of u and v, so you're going to be integrating over the corresponding region d star. Of course, you're going to replace x and y with what they're equal to in terms of u and v. Let's just write it that way. And then there's this, the kind of differential in 2 dimensions is going to be the Jacobian of f. You take so that's the determinant of the matrix of partial derivatives, and you take the absolute value of that times du dv, or dv du. That's the change of variable formula. So let's start with a illustrative example, I guess. Why you want to maybe do this? Okay. So remember that. So we're going to do an example where we want to make the region of integration simpler in the new coordinate system. So we have 2 curves here and a line and another line. Okay. So I'm going to write down the equations of these curves. So this is where x times y equals 1. And this might be where x times y equals, what did I decide finally? 3. Okay, so this will be the line where y equals x. And this is the line where y equals, let's keep it simple, I guess, 2x. And we want to find the area of region D. Now, would this integral be easy to, I mean, this integral would not be easy to set up in the xy plane, right? The domain of integration is too goofy. It's possible. So can we think of a new coordinate system where the region of integration is simple? Okay. Well, what's outstanding about points on these 2 hyperbolas? Right? Well, if you take any point, you take the x and y coordinate on that hyperbola, you take the coordinates and you multiply them, what would you have to get? So what would be a good choice for u to equal so that this hyperbola becomes a nice straight line in the UV plane? Any guesses? If in the UV plane, in the new coordinate system, we want u to be a constant, when in the xy plane we're on this hyperbola, what would we let u equal? Okay. Well, let me just say, if we let u equal to x times y, what does this hyperbola become in the UV plane? Well, it becomes the line u equals 1, yeah. So that would correspond to a line u equals 1. Okay. What about the other hyperbola there? What would u equal then? U would equal to 3, right? So if you take any points on this hyperbola where x times y equals 3, in the new coordinate system, that would correspond to u being equal to 3. Okay, so what do you think we should let v equal to? You could make it y, but there's something even. So suppose I'm going to say that I want to get a rectangle on the UV plane corresponding. Well, I want to get a rectangle. So imagine here I can think of this as y divided by x equals 2. And this I can think of as y divided by x equals 1. Yeah. So I can again use the same ideas that I can make this this line, where y equals x. I could make that be a constant in the new coordinate system if I simply define v to be y over x. So this line here becomes where v equals 1. And this line over here is where v equals 2. And so indeed, we would expect D star to be a nice rectangle. So we've straightened out that region of integration. Yeah, that's one way to think of it. But again, the idea is that D star is way simpler, right? It doesn't have to be a rectangle, but it's at least simpler. Okay. All right. So now we want to use the change of variable. So so first of all, the integral over D, that would give me area of that region. So I wanted area of region D. That would be the integral over region D. And I'm just integrating the area, the differential amount of area, right? Dx times dy. Okay. But when you do this change of variable, notice that in the formula, x and y need to be functions of u and v before you can compute this Jacobian, right? Because remember that the Jacobian is the determinant of the partial derivative of x with respect to u. The derivative of x with respect to v, and then derivative of y with respect to u, and the derivative of y with respect to v. Okay. So x and y are the ones that need to be functions of u and v, not the other way around. Right? So in the theorem, they always draw this picture for students to make sure you know that we're taking points in the UV plane, putting them in a function to get the corresponding xy plane. Right now, we don't have that. Here we have u and v are functions of x and y. So that's the wrong direction. So what can we do? Well, I'll try to solve for x and y. Or you can use implicit differentiation if you'd like. Okay. But anyway, so we have x times y equals u, and then we can rewrite this and say that y is equal to v times x, right? I just multiply both sides by x. Now, notice that neither x nor y are everything's positive. Nothing's zero, nothing's negative in our domain. So we can just divide one by the other, say, or substitute. Doesn't matter how you think of it. Okay. So you get that x squared is equal to u divided by v. So x will be the square root of u divided by the square root of v. Now that we know x, we can plug it in, and we see that y would be square root of u times square root of v. Anyway, so we can try to solve for x and y in terms of u and v. So there you go. We have x and y are a function of u and v. Okay. So now we can go to our change of variable formula and compute this Jacobian. So the derivative of x with respect to u. Let me write that down just to make sure we're following. Okay. Next, the derivative of x with respect to v. So now the derivative of y with respect to u. Something went wrong. Hold on, what did I do? It's supposed to be positive 1/2. Let's rewrite. And then the derivative of y with respect to v. And so the Jacobian is the determinant of that derivative. So we compute the determinant and get a quarter. Let's see, u to the 0. Oh no, I did something wrong. Okay. V to the -1 minus, and then a negative, so plus. Okay. So we get 1/2 times 1 over v. Okay. All right. So that's the Jacobian. And then we would take the absolute value of it. That's what the little bars are there to remind you of. It's absolute value. Did you do substitution? I mean, like over here? How did I solve for x and y in terms of u and v? Well, I essentially plugged in, we substituted for y. Right, so we got that x times y now becomes x times v times x equals u. So that's x squared is equal to u divided by v. So x was the square root of u over v. Or if you'd like, x is u to the 1/2 times v to the -1/2. So that's what I did. And of course, that then allowed me to solve for y as well. right, so now we're ready. So this is the integral over d star, the absolute value of the Jacobian times, say, dvd, right? So that's now easy to do. Let me rewrite it here. So dA became the absolute value of the Jacobian of our function times dv du or whatever. We found that the absolute value of our Jacobian was 1/2 over 1 absolute value of v. But d star has very easy bounds now. Determine that d star is a rectangle, so u goes from 1 to 3, and v goes from 1 to 2. Notice that v is positive, so you can just drop the absolute value bars. All right. So integrating with respect to v, we get natural log of v from 1 to 2. Log of 1 is 0. So integrating with respect to u, get u. So that looks like it's natural log of 2 is the area. All right. Okay. So that was kind of just like kind of contrived, but you see the principle involved. So finding the change of variable that makes your region nice is not so easy. But there are some standard things that you'd want to know. So for example, you can take any parallelogram in the xy. Let's say let's start with the parallelogram at the vertex at the origin. Okay. So here's the parallelogram with one of the vertices at the origin. You can always find a linear transformation that will map a unit square into that parallelogram. Okay. And here, so there's always a linear transformation. So we'll call it T for linear transformation. And why is this linear transformation especially easy to find? Well, you can use your knowledge of linear algebra, right? If you take the standard basis vector 1, 0 here, it should map to this vector. Okay. So this should be the transformation of the vector 1, 0. So you see what we're doing. We're taking this vector and we're applying a transformation so that it becomes this vector in the xy plane. So let me draw that. This standard basis vector should become this new vector. And so similarly, this other basis vector should become this vector in the xy plane. So this should be the transformation of 0, 1. So suppose we have a parallelogram in the xy plane with vertices 0, 0, 2, 1, 1, 3. And then this would have to be 1, 3, so 3, 4. Yeah. And I have some integral. I guess let's say it's 3x, the integral of 3x minus y over the region D. And we do a change of variable so that D becomes this nice unit square. Well, we first need to find a transformation from this unit square into this parallelogram. That's simple. This has to be mapped to this vector, which is, has to be 2, 1. And J over here has to be mapped to this vector, so which is 1, 3. Okay. So the transformation of UV is just the matrix 2, 1, 1, 3. If you recall, that every linear transformation has a matrix representation. And you just need to know what how these standard basis vectors are transformed. So there you go. That's a linear transformation. Explicitly, you see that x is equal to 2u plus v by doing the multiplication, and y would be x plus 3y. All right, so now we're ready for the change of variable formula that we found out transformation. Now, by the way, you can confirm that if you take the point 1, 1, right, you would get the point 3, 4. So that would map, linear transformations map segments to map parallelograms to parallels. So ready for the change of variable. And we have 3 times x. Well, we know what to replace x with. It's a direct substitution. You just directly replace the old variables with the new ones. Minus y, and we know exactly what y is in terms of u and v. And then what is the Jacobian here? Well, sure, we can compute it. So the derivative of x with respect to u, with respect to v, derivative of y with respect to u and v. And what do we get back? Well, we just get this matrix back, right? Which has to be, right? A linear transformation always is the derivative of a linear transformation is always just the matrix representing that transformation. And then the determinant of that is 6 minus 1, so 5. Then du dv. All right. And then we have bounds of integration. So it's a unit square, so 0 to 1, 0 to 1. And this simplifies to 6u minus u is 5u. 3v minus 3v is 0. Oh. Yeah, so whatever. So we get 25, integral of u squared. U is 1/2 u squared to the 1/2. So we get, if you do this very simple integral, you get 25 over 2. Right, so the next thing that I was going to talk about, but we're out of time, I was going to talk about what happens if your parallelogram is away from the origin. Like, so if you had the parallelogram, the same one, but further, like it's not at the origin, can you still do this mapping? Yeah, you just have to translate. So you first say, well, what's the, imagine we have that parallelogram at the origin. That would be a linear transformation. And then you do a translation to the new point. Yeah, but that's for next time, I guess. Then we have to talk about polar and, all right. All right, thank you.